Okay, this is the practice test for MAC1140 Pre-Calculus. We're going over the topics for Exam 2, which covers sections 5.1 through 5.6 and 5.8. In this video, we're going to pick up with problem number 45 on the practice test. So in problem number 45 and the next few problems, they ask you to find the domain of the function. And what you have to remember is the domain of a function is only defined for numbers greater than 0. So for instance, just to remind you, when you're taking a log of 0, see how that's undefined? So it cannot be 0. It also cannot be negative. Log of any kind of a negative number. Whoops. Log of a negative number. See, that's undefined also. So that means that the argument, which is this part right here, which is how we determine the domain, we look at this part called the argument, and we keep it above 0, greater than 0. Okay, so in this case, since that expression is just linear, that's pretty easy. Just solve for x, and you would get x is greater than negative 9. Because when you move this over here, it becomes a negative 9. So x has to be anything greater than negative 9. So if you're going to put that in interval notation, it would be, this is just to give you a visual, here's negative 9. Things that are greater than negative 9 would be everything from negative 9 to infinity. Okay, so that is negative 9 to infinity in interval notation. So that is A. Okay, moving on to 46. Take this. So moving on to 46. Again, same type of problem. Regardless of the base, you need this argument to be greater than 0 if it's any kind of a log expression, natural log any base. So here we're going to take 4 minus x squared and figure out what keeps that expression greater than 0. Now, since this is second degree, this is one of the type of problems that we have talked about in previous sections where you need cut points in order to figure out what the values are for a second degree or higher inequality. So, to get the cut points, you factor. So this would be square root of that is 2. Square root of this is x. 1 gets a plus, 1 gets a minus, because you're factoring the difference of squares. In other words, you can take the square root of that, take the square root of that. So figuring out what makes these 0, because when you figure out what makes these factors 0, you're actually finding the cut points. The zeros are the cut points. Okay, so just by observation, what would make this factor 0 would be negative 2. And what would make this factor equal to 0 would be positive 2. So not only are these called the zeros, but they also represent the cut points on a number line. And that cut points is where we start when we're trying to solve an inequality, second degree or higher. So here's your number line. Go put those cut points and nothing more than the cut points, because you put any extra numbers, you're going to have extra intervals. Okay, so if you have 2 cut points, that means you have 3 intervals to test. So in this region, I think I'll test negative 3. In this region, in between negative 2 and 2, I'm going to test 0. And then over here, I'll test positive 3. Now I'm going to figure out which of the regions have numbers that satisfy this inequality, because those are the only numbers that are in the domain. Only the numbers that keep that argument greater than 0. Okay, so let's see. If I was going to test 3 in the original inequality, 4 minus x squared is greater than 0, it would be 4 minus, I'm testing negative 3, 4 minus x squared, is that greater than 0? This would be 4 minus 9, because negative 3 times negative 3 is 9. This would be negative 5, and that most definitely is not greater than 0. No negatives are greater than 0. So no to any of the numbers in this region. Okay, moving on to testing 0. If I was going to test 0, again in the original inequality, it would be 4 minus 0 squared. Is that greater than 0? Well, 4 take away nothing is just 4, and that is greater than 0. So yes to anything in this middle region. Okay, then last number that I'm going to check out is positive 3. And I'm going to see whether or not that works. So I'll test it right here. 4 minus 3 squared, and I'm sure you can see already that you're going to get the same answer as when you plugged in negative 3, because whether you square negative 3 or positive 3, you're getting a positive 9. And by the time you go 4 minus 9, you're into negative 5, and that is not greater than 0. So no to any of the answers here. So the only values that work as a solution for 4 minus x squared is greater than or equal to 0 are the numbers between negative 2 and 2. And since this doesn't have a little equal sign, a partial equal sign in the inequality, these will be parentheses around the endpoints. So you're talking about negative 2 to 2. Okay, for number 46, and that would be choice A. Okay, and now let me try to move over to paper because I'm already running into the next problem. Just let me grab some paper here. Okay. Alrighty, for 47. Okay, for 47, you're into the same problem. You're still looking for the domain. This belongs to that same group of problems. So here the argument is, again, whether it's log, whatever base, or natural log with a base of e, you need to keep that argument above 0, greater than 0. So we want to keep x plus 5 over x minus 7 greater than 0. And this was another type of inequality that requires cut points. Second degree or higher inequalities require the cut point method, and rational inequalities require cut points. So we need to keep that above 0, and the way you get the cut points this time is you figure out what zeroes out the numerator, what zeroes out the denominator. So the cut points are the following. Okay, the 0 of the numerator is negative 5. And the 0 of the denominator is 7. So those produce the cut points on the number line, negative 5 and 7, and just the way you would test each of the intervals created by these cut points, as we did in the last problem, you do the same thing here. So here I might test, it's your choice, I'm going to test negative 6. In between any negative and a positive, the 0 occurs, and that's always really easy to check, so I choose that. And then to the right of 7, the smallest thing I can test is the number 8. Okay, so testing in this original inequality, knowing that we want to keep it greater than 0, we're looking for anything any test value that I plug in that results in a value greater than 0. So I'm going to plug in my -6 plus 5. And then here's a spot for x again, -6 minus 7. And that is equal to -1 at the top and -13 at the bottom, which is just 1/13. And that is definitely greater than 0. Okay, so yes for this. And then we're going to go and test the 0. And that would be 0 plus 5 over 0 take away 7. Is that greater than 0? And this would be 5 over -7. No, there's no negatives that are greater than 0, so this is not true. I said no. When you plug in a 0 or any number in this interval, you get numbers that don't work. Okay, next thing is to test the rightmost interval, which is where we're getting the 8 from. So it would be 8 plus 5, and then 8 minus 7. Okay, that would be 13 over 1, which is greater than 0. So yes to this interval of numbers as well. Okay, so we have numbers that work here, we have numbers that work here, and then we're going to just talk about those intervals that have yeses, that have numbers that work. So this represents anything from -infinity to -5. You have to jump over this region, so you have to say anything in here works, or you say or using a union symbol, or anything in this interval works, anything from 7 to positive infinity. Okay, so that is your final solution right there. Okay, as far as the choices go, that would be -infinity to -5 or 7 to infinity. So choice B. Okay, throughout this practice test, I'm going to keep emphasizing that I've made multiple choice questions on the practice test just for ease of checking your answers quickly. On the real test, you will have a few multiple choice, approximately 15%, and the rest of the test will be free response. Okay, moving on to the graphs. I don't know how crazy you really need to go with the graphs. You do need to know you have to have some basic knowledge of shifting. What produces a horizontal shift? In other words, making the graph go right or left. Those are horizontal shifts. You have to know how to identify them and what they look like in an equation. You also have to have knowledge of the parent graph. So when you're talking about a parent logarithmic graph, okay, and just knowing this is going to help you pick these answers without too much struggle. Like in 48, parent logarithmic graph, the logarithmic graphs are the inverse. They are the inverse graphs of the exponential graphs. So when you're talking about any kind of an exponential graph, it looks like this. Like if you were going, let's say, f of x, any base bigger than 1, something like that. What happens with that is right here at the one that's on the y-axis, it goes right through there. The x-axis acts as the asymptote, and then it just climbs upward, climbs out that way, goes to -infinity. That is what y to the 2x looks like. Well, the inverse graphs are, let's see, if you were going to try and do the inverse here, it would be log of instance, if you were going to do this, okay, so if you were going to try and put this in logarithmic form, you would take the number that plays the role of the base in the exponential expression, and it would become the base of the logarithm. And then these two things would switch sides. So the x would no longer be on the same side with the 2. It would be over here by itself, and the y would be right here. So the difference between the exponential graph and its inverse, called the logarithmic graph, is that the x's and the y's change behavior. So instead of it having this asymptote at y equal to 0, which is the x-axis right here, and instead of it going through 0, 1, all of that switches. Now it goes through 1, 0. These two switch. So now it goes through 1, 0 instead of that. And instead of having the asymptote, or one tail, fluttering above the x-axis, now instead of the x-axis serving as the horizontal asymptote, now the y-axis serves as the horizontal, the vertical asymptote. And the graph looks like this. And if you recall, whenever you're talking about any graph and its inverse, and this is the inverse, this log of y base 2 equal to x. This is the inverse of this graph, and you can tell because if you go right through y equal to x, you have mirror images on either side of this line called y is equal to x, and that is always true of any two graphs that are inverses. So make sure that you know what the parent graph looks like, okay? We have switched over, and you're going to switch over too as you take the test, from exponential graphs, which did this, and we did, quite a few graphs in this practice test, to this graph right here. Now we're concentrating on the logarithmic graph, and you can use key points like this 1, 0 that you see right here, and shift your graph right from there. Just understand that this tail goes down and this one climbs to infinity. And when you're doing a flip or when you're doing a horizontal shift, you can think about this point. If you're going to shift to the right, it goes this way. If you're going to shift to the left, it comes this way. If you're going to flip it over, instead of this tail going down along the y-axis, this is if you're going to flip it across the x-axis, like rotate it right at that point. If you're going to flip that kind of graph, then this would go up instead of down, but it would still flutter along this y-axis, using the y-axis as the asymptote. These graphs can also be flipped over the y-axis. It's all a matter of where the negative is. Okay, so right now we are concentrating on this graph right here. I just wanted to tie it into the exponential graph. This is y, this is x, and the basic logarithmic graph goes like this. It uses the y-axis as its asymptote. So in other words, it gets closer and closer and closer, and then one tail goes off into infinity. Okay, so now, knowing that, and you can also use your calculator for these graphs. Okay, so looking at this graph right here and knowing that this is what the parent graph looks like. If this is the parent graph and you see that this is lower than the parent graph, then what happened here is a vertical shift has occurred. Vertical shift, you can see that it is lower. Now with vertical shifts, the sign in the equation is the same as the action that you can see occurring in the graph. This graph appears as though it has come down approximately 3 units, or exactly 3 units. The point that would have been right there in the parent graph, where it would have cut right through there and climbed upward, that point is now lower. Now it's down here. So it's you're going to see a vertical shift of -3. The graph has moved down 3 units. So what does that look like in an equation? Not that, because when the 3 is with the x in parentheses, that's what it looks like in an equation when the graph has a horizontal shift. Your graph does not have a horizontal shift. This graph that you're seeing right here compared to the parent graph, that's a vertical shift. It's lower than the parent graph. Okay, that would not be a vertical shift of -3, because when you rewrite this, that 3 that you're seeing there is +3. Okay, so it can't be this one, can't be this one. This would be something with a vertical shift. The vertical shift is always a constant that is not part of the x expression. And when they want to imply that the number is part of the x expression, they'll wrap the number and the x in parentheses. So this is just a free agent on its own. It is not part of that x expression. So this is a vertical shift. And because it's negative, we know that it goes 3 units down. Vertical shifts, what the sign does, what the sign implies is what the graph actually does. That's not true for horizontal shifts because they're the opposite. Okay, so it would have to be that one right there. So 48 is C. All right, moving on to 49. Now let's see what 49 is doing. Now this graph compared to the parent graph, you know that the parent graph usually goes through 0, 1. What would that parent graph look like? What would have had to have happened to the parent graph for it to now look like this? Well, I think that you can see that this graph is pushed over a certain number of units to the right. How many units? Well, it usually goes through 0, 1. And now that turning point right there is at 4. So instead of turning right here and fluttering against that y-axis, the entire graph has moved over. And it has moved over 1, 2, 3 spaces. Okay, this is a horizontal shift that you're seeing. 3 units to the right of where it usually is. Now, usually when you move to the right, that indicates, you might think, oh, that's a positive shift. But horizontal shifts in the graph, they behave the opposite of what the sign is when it's in the equation. So if you're moving to the right and you're thinking that means +3, it's really -3 in the equation. Okay, so that is not a -3. And it's got to be a number that's included in the expression for x in parentheses. So that's not it because that's a +3. And I'm looking for something with a -3. This is not even included with the x, so it can't be that. And this is it right here. This is a -3. It is included with the x in parentheses. So this is what you're talking about. This is a horizontal shift because it's part of the x expression. It's a -3, but acts as a positive shift of +3 to the right. Remember, this and this will be the opposite for horizontal shifts. So again, choice C for this one. You could also put it in, but then you'd have to put each one in your calculator. That's why it's better just to have a working knowledge of the shifts. Okay, here's one right here. And as I said, this is what the parent graph looks like for any logarithmic graph. It goes like this. It asymptotes against that y-axis, and then it goes through 0, 1. So one tail just goes down, down, down. If you were to take this tail and flip it across the x-axis, just rotate it right, spin it right across the x-axis, then instead of this going down, it would be going up like this. It would just go up this way. This tail right here would go up. Okay, so you want to look for a graph that looks like this, and you know the rest of it would be like this. You would be just taking this and spinning it across the x-axis. That is what's happening here. Now, what causes that to happen? Spin across the x-axis. That happens when there is a negative out in front of the expression that creates the actual shape that you're working with. We're working with the shape produced by the logarithmic expression. So not that. This, when you have a negative in front of the x, that spins it across the y-axis. And as I said, you could put these in your calculator just to confirm what I'm saying. This is the normal logarithmic expression, and that doesn't look like it, so it can't be that. Can't be this. This has too many rotations. All that's happening here is that this thing went from the way it usually is, and then once it's spun over the x-axis, it's now, this tail is now going up, and instead of this going up and to the right, it goes down and to the right. Okay, so that would be this graph right here. The multiplier should be out in front of the expression that creates the shape. It'll be found right out here as a coefficient. So for 50, the answer is D. And you know, like a good thing with your graphing calculator, so you can just, you know, compare it. You can put y is equal to, there's log of x. We're thinking that this is what would make it look like that. And you really, they don't show you like the tail here, but it really is like just to the side of that. You just can't see it when it's done in a graph, you know, graphing calculator. So let's see, let's go put in negative log of x, close that, and you'll be able to see both graphs. It's going to graph this one first, the parent graph, and then it's going to graph this one so you can see what happens. Oops. You fix the window. These are the two buttons that you use when you're going to graph. You can use zoom standard, and then you can adjust from there. That's the normal graph. Goes up that way. Yeah, you can't see it here. I'm going to put less numbers on this so you can see it a little bit better. Like less of this. So window, so I'm only going to go to about -2 on that side. Let's see what it looks like now. Okay, there's the normal one up and to the right, and it skims along this axis. Then this one goes down and to the right and goes like this. Flutters right next to the positive y-axis. Okay, so that's choice D. 51. This time, what's happened is that instead of it looking like the normal parent graph, which again is this is a very visual thing, although you're not even using your visual senses if you're just putting it in your calculator. But if you were to take this and flip it across the y-axis, instead of going up and to the right, it would go that way. It would look like this. This is what it looks like when you take this whole graph and flip it across the y-axis. And it looks like that. Okay, that happens when the negative is with the x. Okay, so when the negative is out front, it just flips over the x-axis, the whole graph. Spins over the x-axis. But when the negative is with the y, it flips across the y-axis. So that would be this one. 1 is A. Okay, going to 52, graph the function. Here we have a couple of different things that are happening. We are going to, because the negative is in front of the logarithmic expression, we're going to flip over the x-axis. That's called a reflection about the x-axis. That's the way they phrase it in the books. And you can even rewrite this if you're more comfortable looking at it like this. That negative in front of the logarithmic expression, this just happens to be a log with base e, which is why it has ln instead of log. And then that is a -3. Okay, that -3 is your vertical shift. Vertical shifts behave exactly as the sign implies. Horizontal shifts don't. So this is going to go down 3 units. And then that negative is going to flip it over the x-axis. So think about it being lower than it usually is. Now let's think about what it usually looks like. This is what a normal logarithmic graph looks like. Flutters against that negative y-axis, using it as the asymptote, goes through 1, 0, off to infinity. So if we're going to take that and flip it over the x-axis, like spin it over the x-axis, then it's going to look like this for one thing. That's one thing that's going to happen. Then on top of that, you're going to take that graph, this flipped graph right here, and you're going to move 3 units down because of that vertical shift. So this is going to move 1, 2, 3 units down like that. So it's going to be lower than it usually is. Even though it's going to go up and down this way, it's going to be that turning point. Instead of it being right there, it's going to be 3 units lower than it usually is. So that graph, this goes up and down. So this is a good potential. And that turning point is right down here at -3. So 52 looks like it's going to be A. This is flipped over and it's lower than it usually is. This is higher than it usually is. Can't be that. That shows a vertical shift. This shows a horizontal shift. That's not what's going on. And this is going through 0, 1. That turning point should have been lower. Okay, so A. Put them in your calculator if, that's what you need to do. Okay, this particular problem, all this is you can even rewrite it if you want. You got your log expression, nothing going on there with negatives or anything. The base is irrelevant, and you have a +2. So all that's happening here is that normal log graph that goes right through 1, 0. This is just what we call the parent graph, and we always think about the answers with respect to the parent graph. Well, all that's happening here is a vertical shift. So the one you pick should be 2 units higher than this one. Just take this and lift it up 2 units. That point would be like that, and then it would be like that, but still using that y-axis as the asymptote. So let's see, which one looks higher here? This looks like it has a horizontal shift. It looks like it's shifted so that the point that it cuts through is over here. So it's not that one. This looks like it has shifted 3 units to the right. You don't have a horizontal shift. These are both using the y-axis as the vertical asymptote, only this one goes through 0, 1, and this one has a turning point that's 2 units up in the air. So this one is showing a vertical shift of +2. That is 2 units higher than it usually is. Okay, so 53, that would be A. Okay, moving to 54. In problem 54, you have 3 different things going on. You may want to use your calculator for this. You may want to try and reason it out. It's up to you. You can put these in your calculator, but what's going to happen is it's going to flip over the x-axis. It's going to, this right here is going to make it flip over the x-axis. That's one thing that's going to happen. This is going to make it vertically shift, and because it's a positive 2, it's going to vertically shift up 2 units. It'll be 2 units higher than it typically is. And this is going to make it have a horizontal shift. Remember, the horizontal shifts behave the opposite of what you see in the equation. A horizontal shift of -4. There's quite a few things that are happening. Now, if you are going to try to reason it out, comparing it to the parent graph, that's what the parent graph looks like. So I'm going to do one thing at a time here. If I was to flip this over, then this tail, instead of going down, would go up, and this would come out like this. So it would use the upper y-axis as the asymptote instead of the lower x-axis, the negative x-axis as its asymptote. So now the asymptote's up here. And so that's just it flipping over. Then there's other things going on. This point would be shifted 2 units up. And that turning point would be shifted 4 units to the left. So I know it's going to go like this. So from this point right here, this 0, 1 point, if I wanted to shift that 2 units up and 4 units to the left, because this is your horizontal shift, if you know it behaves the opposite of what it looks like in the equation, that means you're shifting 4 units left because you're respecting a -4 horizontal shift, not a +4. So this turning point, not only does it flip over, which I've already demonstrated right here, but that turning point is going to be 2 units higher and 4 units to the left of where it usually is. Here's 2 units higher, 1, 2, because this is the point where it usually turns at if it was the parent graph. So go up 2, and then take that point 4 units to the left, and then make the graph like this. Sail coming up and going down like that. So you're basically looking for a graph like that. Okay, that would appear to be, let's see, choice, before is choice A. Okay, this is too low. Okay, it should be, the turning point should be higher than it typically is, and 4 units to the left of where it typically is. So usually it's right here. So this turning point is at 2 right there, but instead of it being right here at 0, 1, it's 4 units this way. Okay, so it is choice A. And plus it's flipped. It's going up instead of down like the parent graph usually does. This is signifying a flip. Okay, again, put it in your calculator if that's what you need to do. There's too many shifts. Okay, moving to using the properties, which are very important in solving logarithmic equations. Okay, so in 55, use the properties of logarithms to find the exact value. So what you could do here is, because there's a plus sign, there was a property that says when you have 2 separate logs, both with the same base and a plus sign in between them, they can be written as a single logarithm as long as they have the same base, and these do, but as a product. So this would be product of this argument and this argument. 14 times 17. Okay, which is equal to log of 14 times 17 is 238. So your new argument is 238 and your base is 238. Well, that brings to mind another property. We just used the property that when you have a sum of two logs, you can bring them in together as a single log as long as you multiply their arguments. And they have to have the same base, which these did. Each of these separate logs had a base of 238. There's another property called the inverse property, and that says when the argument matches the base, they take each other and cancel each other, take the log with it, and the power that is on the argument, which is a 1, you have 238 to a power of 1 because there's no power there. That is what this entire expression evaluates to. That's what it simplifies to, whatever is in this power position. So this is equal to 1, and that is choice B for 55. Okay, moving to number 56. 56, same thing. This is another version of the inverse property. If the base here matches the base here, then those cancel, take the log with it, and the number in this argument position is what it simplifies to. So 56 is equal to 9, and that is choice C. Okay, moving on to 57. 57, you actually have log of 12 minus 2. Now, when you don't see a base, that base is said to be 10. So I'm going to rewrite this. This is going to be 10 raised up to a power of, I'm going to combine these two because they do have the same base. Again, when no base is written on log, that base is said to be 10. Since there is a minus sign in between these two separate logs that play the role of the exponent, you can combine them into a single log. Okay, two separate logs separated by a minus sign combined into a difference. Okay, now all of this is happening up in the power position. Okay, so I'm going to take 12 divided by 2. If there is a minus sign separating the logs, that means they used to be a quotient. Okay, remember that base is 10. Let's keep going with that. So we have 10 raised up to a power of log. The power just happens to be a log. Log of 6, 12 divided by 2 is 6, with a base of 10. Well, same thing that I used in problem 56, and that was, I know I did a lot of marking on top of everything so you can't really see it, but when this base right there matches that, they cancel with each other, and that's exactly what's happening in this problem. This base matches this base, they cancel, they take the word log with it, and the number in the argument position is what it simplifies to. So that would be choice C. Okay, moving on to 58. In problem 58, we have log of a quotient, and we can take that apart. This says write as a sum or a difference. If it's a quotient, it can be written as a difference. So this would be equal to log of the top, 14 times square root of x, base 5, minus log of y, base 5. And you can keep going with that because you can deconstruct this product as well. When you have log of a product, it can be deconstructed into a sum. So it would be log of 14 base 5 plus log of square root of x base 5 plus log of y base 5. And then you can still do one more property. So we had a quotient which deconstructs into a minus sign. We had a product which deconstructs into a sum. And then we also have the power property right here, because this middle term is the same thing as log of base 5 x to the 1/2. When you express the square root of x but in power form, it's x to the 1/2. And that power, according to the power property for logs, comes out and acts as the coefficient. So it would be 1/2 times log of x base 5 once you bring that 1/2 down in front as a coefficient, and then bring down these other terms. So that had all the properties for logs, almost all of them. It didn't have the inverse property in it. Plus log of y base 5. That's using all the properties to the fullest extent. So for 58, the choice that has that answer would be, let's see, let me check them out. Oops, I didn't copy this sign right. This was a minus in front of that term. So the log of y term had a minus in it. Let me fix that. Okay, so it should be, and that was because this was the denominator, and that's the one that gets the minus in front of it. So when you're deconstructing this quotient, it's log of the top minus log of the bottom. So I should have continued carrying that down. So that would make it choice C. Okay, moving to 59. Again, we have a quotient, and we're going to start by deconstructing that quotient. So it's log of the numerator, keep that entire numerator together, base 4, minus, separate it from my answer here, minus log of the denominator. And the denominator always has a minus in it when you're deconstructing a quotient. Then you can take the power property and apply it right here. So this would be equal to log of x plus 6. This is also base 4. Log of x plus 6 base 4 minus, take this power, bring it down in front of the log as a coefficient. Okay, you're never going to leave that power on there when they're asking you to use the sum and difference formulas. When they're asking you to use the properties, because that's the power property. Okay, so now you've deconstructed the quotient and you've also brought down the power. And that answer for number 59 would be C. Okay, moving to 60. Problem number 60, you're going to express as a single logarithm. So now you're taking it back into single log form. So this is going to be, separate this from the other answer. Okay, first of all, if there's a coefficient, that means that it used to be the power right there. So this would be log of q to the 6th with a base of b minus log of r with a base of b. And if there's a minus sign separating these two terms, that means that as a single log, it was a quotient. Whenever there's a minus. So what comes before the minus sign is the numerator. And what comes after the minus sign is the denominator. And then put that common base. Okay, so number 60 should be, so let's see, which one is it? This one. Let's see. Okay, moving to 61. Problem 61, we're also going to express that as a single log. So I think I'm going to bring these powers up first. So this will be x cubed. This 5 will be the power on this argument. So power 5, and then there's a plus sign separating them. So that means that as a single log, this was log of x cubed forming a product because there's a plus sign between the terms, times x minus 6 to the 5th with that common base of 6. Okay, and that would be choice D. Okay, moving to 62. Problem 62, bring that together as a single log. Now you have a mixtures of pluses and minuses. So let's see. And one of these terms does not have a base of A. So what you want to try and do is rewrite this with a base of A. So let's see. Hold on for 1 second with that problem. I'm going to stop this video. Let me stop this video here. I'm going to pick up with problem 62 in the next one.